Hello everyone. My name is Pierre-Alexandre Duverne. I'm currently a postdoc at APC in Paris, France. So first of all, thank you for inviting me for presenting this work that has been conducting with several persons, including my former intern, Wafa Mouissi, on optical forward strategy for the next neutrino detected galactic core collapse supernova. So for this presentation, I will try to give a short introduction, describe the simulation setup we developed for addressing this work, and eventually to discuss some of the results we had. During this presentation, I may use some acronyms, so I've defined some of them here. If at some point during the presentation you want to ask questions, please do not hesitate to do so. So the main motivation behind this work was trying to address how is it possible to organize an optical follow-up campaign for trying to find electromagnetic counterparts after neutrino have been detected after they have been emitted by a galactic supernova. And the general idea behind this organization is that in order to maximize the scientific output for the next galactic core collapse supernova, it requires preparation and coordination between all the follow-up all the telescopes participating in the follow-up campaign. And to address these, problematics, we first started by generating a population of galactic supernovae, namely position, electromagnetic light curve, extinction, and so on. Then generated a bunch of localization of the neutrino burst with a network of different neutrino detectors, and eventually simulated follow-up campaigns with both the Rubin telescopes and the Tarot facilities that are small robotic instruments. As you may know, this work is available on preprint as a preprint on archive. So if you want to have more details, please have a look at that manuscript. So multi-messenger astronomy based on neutrinos started in 1987 with the detection of the famous supernova SN 1987A, for which that happened in the Large Hadron Cloud. And it was discovered first in the optical domain. And it turned out that this event was also detected by three detectors in the neutrino domain by IMB, Kamiokande, and BNO. And this coincidence allowed to start a multi-wavelength follow-up campaign that led to the characterization of this supernova and of its remnant to this day, because it's still very bright and very studied. Ideally, in a campaign right now, for trying to find a supernova in the galaxy plane, it would be the other way around. We would have start first the neutrino signals detected and then the follow-up campaign. And these events showed their potential with multi-messenger astronomy, with neutrino, but with multi-messenger astronomy in general, where you have information that are slightly different in each regime. So for here, the neutrino burst informed about the localization, the explosion time, and provide also information about the cooling mechanisms. And on the electromagnetic side, we have information about the ejected matter, the local environment, and a much more precise localization. And combining all those data, it allows to have a global picture of astrophysical events that you wouldn't have if you had only one of the messenger. Right now, for the current multi-messenger landscape for neutrino observation, we have on the neutrino side several facilities that are either existing, such as IceCube, Super Kamiokande, or CamSoNet, and some that are either in construction or being planned to be in construction, such as, well, also CamSoNet, for example, that is still in development, Hyper-Kamiokande, or Juno. You also have SNEWS, obviously, you know that is sending alerts in case some alerts looks like there is a galactic supernova happening somewhere. On the optical side, you have typically two different type of facilities. The large field of view facilities that are doing surveys, such as ETF, SSSN, or Rubin, that are just scanning the sky continuously, trying to trying to find new objects appearing in the sky, in the transient sky. And we also have a consortium of small instruments that are trying to respond to external alerts. So usually it's GRB or gravitational wave, but also neutrino. And this is the case, for example, for the Gamma collaboration. So now that we have an idea of the motivation behind this work, I think I will go now to the description of the simulation setup we use for this work. At the heart of this work, we have this core collapse supernova population that consists of 500 supernovae distributed in the Milky Way following this spatial distribution that is made of two exponential distribution. That follows the Adams and collaborator paper in 2013 that has been designed based on population evolution codes. We also splitted these 500 supernovae to three progenitors, so the red supergiant, blue supergiant, and Wolf-Rayet stars. And to estimate the fraction of each progenitor, we referred to a bunch of population study of these type of stars based on observation in the Milky Way and the surrounding satellites, galaxies. And this paper identified two regions, so the galactic center that corresponds mostly to the innermost part of the galactic plane that contained a bulge, and the galactic anti-center, which corresponds to the outermost part of the galactic plane. And eventually we had 342 red supergiant, 107 blue supergiant, and 51 Wolf-Rayet stars. The next thing we had to include in our work is the estimation of the extension of the luminosity of the optical emission emitted by the supernova, because there's a lot of dust spread in the galactic plane. And for that, we use the base star 3D dust map developed by Green and collaborator in 2019. And it allows to estimate the extension over line of sight given a position in the 3D space. However, this map lacks data for declination below minus 30 degrees here, and this is visible on this plot. And unfortunately, it affects a significant part of this population. Almost more than half of these 500 supernovae have no extinction estimated with baseline with the base star map. And to address that, we assume that this dust distribution was symmetric with respect to the galactic plane. And for that, we use this transformation for right ascension and declination for a region where we didn't have any information with base star. And we then filled in that into this region, and we obtain this dust map distribution augmented with this small trick. Right. After that, what we wanted to see to model are the electromagnetic emission, and the first one we're interested in is the shock breakout. So after a core collapse, the collapse makes the innermost layer of the star collapsing onto the center and then bouncing back on the degenerate core. And it creates a shock that is propagated into the outer layers until it reaches the outermost layer and create these flashes in the UV X-ray domain. But part of this flash is also emitted also in the optical wavelength, and this is what's called the shock breakout. It acts as a precursor in the electromagnetic regime for the supernovae, and it's very important to try to find this kind of counterpart, as we have only a few examples so far, and it constitutes an important target for the follow-up campaign. It will inform greatly about the shock propagation and what happened in the innermost part of the supernovae, and also tells us information about progenitor characteristics. As you can see on the right-hand side plot that's provided in Kissler and collaborator paper, the shock breakout characteristics will strongly depend on the progenitor nature. In particular, for Wolf-Rayet star, for example, it will take only 1-2 minutes to propagate. For blue giants, it's more 1 hour, and for red supergiant, it's as the day time scale. And the duration of this shock breakout will also be highly dependent on this progenitor. For Wolf-Rayet, it will last for a second, for a minute, also for blue supergiant, and about an hour for red supergiant. And these are the numbers we use for the rest of this work. One important thing to notice here is that for Wolf-Rayet star, the timing of a minute's delay plus 2 seconds duration is too short to be reasonably expected to be detected by ground-based facility reacting to a neutrino burst. So we didn't consider for Wolf-Rayet that it was possible to observe that. Otherwise, for the red and blue supergiant, we estimated the magnitude, the absolute magnitude of these events to be minus 11 and minus 13 max, respectively, based on early light curve provided in papers for the shock breakout phase. After the shock breakout, we considered that it was a usual light curve template that will be happening. And for that, we consider that for red and blue supergiant, this would look like supernova type 2P and type 1BC for Wolf-Rayet stars based on supernova survey. This survey also allowed us to estimate the absolute peak magnitude for the two different template light curves, and this is shown in that plot, for which we have the normal distribution and with parameter mean and standard deviation estimated with this supernova survey. On the right-hand side plot, you have a temporal diagram summary for the core collapse supernovae electromagnetic evolution, for which the neutrino burst gives the start for the whole event. And then the shock breakout propagates, and there's nothing basically to observe in the electromagnetic domains at that point. Then there's the shock breakout that lasts for some minutes up to 1 hour for a red supergiant. And then we have the usual supernova template. So in orange, it's the 1BC type supernova, and in blue, the 2P type. And now moving on to the neutrino world. When core collapse supernova happen, what we expect is that there's a burst of neutrino emitted in the MEV domain, and this burst is detected by different neutrino detectors on Earth. And using the time of arrival at each facility, it's possible that we can make a triangulation of that signal and estimate the localization based on this information. And after that, it's possible to generate a probability distribution on the sky of the source localization. And this is called what we will call later on a sky map. And this is the basic object we will use for organizing and guiding the follow-up campaign with the optical facilities. And for creating those neutrino localization, we used a tool developed by Alexis Colero and collaborator in 2020, which is called light curve match, for which each detector is modeled as a 2-parameter object, which is the effective mass and the background rate. Then they assumed a neutrino light curve, and based on the characteristic of each detector, they try to estimate time delay uncertainties between each pair of detectors, which allows to make the triangulation of the supernova position. And eventually, we obtain a sky map, so this probability distribution over the whole sky. On the right-hand side, you have an example of the neutrino light curve as it would have been seen by each detector of the paper. So IceCube here, Chemstreet, and SuperK and AlphaK Muconde. For trying to model that there will be different possible network configuration, we try to go for 4 different neutrino network. First one, which is the base case scenario where IceCube, ARCA, AlphaK Muconde, and Juno are observing the neutrino burst. Then, since AlphaK Muconde and Juno are still under construction, consider 2 cases where only one of these 2 facilities is active at the time of the neutrino burst. And a 4th configuration where there's only IceCube, ARCA, and SuperK Muconde, which basically is the current situation for the neutrino network. After that, we use light curve match to generate sky maps for each core collapse supernovae and each network configurations. And this is the kind of object we had. So this is the probability distribution for supernova burst detected by IceCube, ARCA, AlphaK Muconde, and Juno. One important thing we also did afterwards is that since the actual injected position of the supernovae is usually at the center of the most probable region, we randomize that following this sky map distribution in order to avoid biases in the timing estimation for how much time it takes to get on target, because it usually is the most probable region is usually what's first observed by the follow-up campaign, during the follow-up campaign. On the right-hand side plot, you have an examples of one injection and the fourth different sky map depending on which neutrino network is observing this injection. So in black here, you have this ice cube Arca HK Juno configuration, and then in orange, blue, and red, you have the different localization. One important thing to notice here is that when we have four different neutrino detector observing the burst, you have only one region here. Otherwise, the distribution starts to be multimodal because you create more symmetry and degeneracy with only 3 detectors in the timing of arrival region. So repeating that process for all the schema, for all the network configuration and all the core collapse supernova injection, we obtain this distribution for the credible region area. So this is the 50% and the 90% credible region. And one thing we can notice here is that there's a strong dependency on what's the network configuration. In particular, when we have hypercommunicante involved, the sky maps are significantly smaller than when only Super K or Juno are participating in the observation of the neutrino burst. Even though, even in the best case scenario, the typical size we have for 90% credible region is around 150 square degree, which are still very large localization uncertainties. We also discussed previously the fact that we have multimodal distribution for 3 detector networks, which also make the follow-up campaign more difficult. And based on all these simulations setup, we made some observations. At first, we have large localization uncertainties at 100 up to 1,000 square degrees for rapidly evolving transient, especially at the first stages, which are the most important and the most interesting to target when you have a neutrino burst. And we also have short time delay. And if you want to observe the shock breakout emission, that is an important counterpart we want to observe. And all of those elements show that there were some strong similarities between gravitational wave follow-up in the optical domain and the follow-up of core collapse neutrino in core collapse supernovae emitting a neutrino burst in the galactic plane, which means that it will be difficult to organize this, but it also means that there are already some strategy and tools developed for that kind of campaign, and that it will require a lot of coordination between the facilities, but we can use the current tool, which is called GWEMOB, for planning the follow-up observation, which has been developed by Michael Coughlin, collaborator, in 2018. And basically, the idea we used for making the follow-up observation was to use what's called the tiling approach, where basically you want to cover the whole as much as possible of the sky localization map by observing this with large field of view instruments, so at least 1 square degree for the field of view, and look for new object that could be related to your external trigger. So here it's a neutrino burst, but it could be also gravitational wave, for example. And this technique is already widely used by different surveys such as PanStar, ZTF, but also Taro and Rubin is also planning to use that for external alert follow-up. And the idea behind the GWEMOB design is that you have this, probability distribution, and you try to make those images. And GWEMOB Tech has input this sky map and gives you as an output a list of right ascension and excitation position, along with a time when to observe this position. And each observation is modeled with the field of view of the telescope, for which each circle corresponds here to one image made with a constant exposure time using the R filter. We made this choice of filter because it's the most well, it's first very widely used among the optical community, and also one of the most sensitive one in the Earth sky. For the optical facility we use for this work, we use two different ones. So first, the Taro network, which is composed of three small robotic instruments, one in southern France, in Calerne, one in the La Réunion island, and one in Chile. Both TCA and TCH are 4 square degree field of view, and TRE is 16 square degree field of view. The second optical facility we used is Rubin, because it has this wide field of view of 10 square degrees. It can reach very deep depth, around 24 magnitude in 30 seconds, which make it a very strong facility for making this kind of follow-up. For the Taro instrument, we limited our exposure time to 3 minutes instead of 30 seconds for Rubin. It allows us to go to 16 magnitude for TRE and 18 for the two others. So basically, these are all the ingredients we use for the simulation we wanted to implement. And I think now it's time to move on to the results part. So here I will discuss what we call the baseline results, which corresponds to how much time it takes to get on target, regardless of whether or not we detect the supernova. It's just a timing evaluation. And so we generated the observation plan for all the core collapse supernova injection and all the network, neutrino network we discussed earlier. And on this table, what you can observe is that we have a slightly better timing for tau, because we have in median about 3 up to 6 hours to get on the core collapse supernova position after the neutrino burst alert, which is slightly better than Rubin. That's more at the 6-7 hour time delay. Another things we wanted to evaluate was also the number of times, so the number of images you have to take before reaching the target's position. And it's comparable for the two instruments when the sky maps are narrower. So the case is when hyperconic day is detecting the neutrino burst. Otherwise, we have a factor of 2 basically between the number of images you have to take with tau and the number of images you have to take with Rubin. These two results can be explained by, I think, two points. First, tau is much quicker at slewing because they are just 20 centimeters facilities, whereas Rubin is an 8 or 9 meter facility, which is much slower to change from one position to another. And also tau facility are first, there are 3, and also Taro Réunion, so TRE, is as a field of view which is larger than the one of LSST, which helps for getting on target quicker and with less observations. On the right-hand side, you have the distribution of the timing to get on spot for the different neutrino network, and on the left for Rubin, and on the right for Tau. After these initial results, we wanted to get more in depth and try to find when do we detect actually detect the supernovae, because as we have seen earlier, there's a time delay between the neutrino burst and the time when the first light emitted by the shock breakout. And as we have recalled here, this delay can be up to 1 day for red supergiant, which means that even if you react very quickly, you can arrive on spot before any light is emitted. So you won't detect anything despite having observed the right position. So we gave it some detection criteria. So for detecting the shock breakout, we wanted to check that the core collapse supernova position is imaged in that time interval, so between the shock breakout delay and the shock breakout delay plus its duration. And on the right-hand side, you have the distribution of the shock breakout magnitude after it's been corrected for the distance and the extinction. And what you can see is that the faintest one are about 15th magnitude, which are brighter than the 16 magnitude limiting 16 magnitude limiting magnitude of theory, and the other are even deeper. So there's no issue for the exposure time here. And next thing we considered is that if we image the core collapse supernova position after the shock breakout delay plus shock breakout direction, we just consider that the supernova was detected at the magnitude of the template light curve we discussed in the first slides. Otherwise, if we were, for example, before the shock breakout delay, we consider that there was no detection, and then we repeated the process of generating the observing plane, reducing it, trying to find whether or not the observation of the core collapse supernova position happened in the right interval. And if no, because as you can see here for red spur giants, this is slightly more than a day, it's 1.2 days, I think. And so there was also cases where we were still too on target too early. So we repeated that for a third night by generating again these observation plan. These results are summarized in this table on the right-hand side, where you have for each network configuration the number of shock breakout or just usual template light curve detected for each night of observation. So for here, we have a detection of the shock breakout by Ruby in the second night, and then this is number of core collapse supernova detected after the shock breakout, for a total of 358 detection of the electromagnetic counterpart. And for this column, you have the same information, but for tau this time. Another thing we evaluated at that point was what's the magnitude of the supernovae when we detected it. And basically, the results are the same for all the configuration and all the and for both Ruby and tau, which is basically we observe at in median 8.5 magnitude, which make this detection very bright objects. And so this won't be actually a problem for Rubin. There's a limited number of cases where maybe tau sensitivity is too faint or too shallow, sorry, for detecting completely the supernovae, because it happens at magnitude above 18th, but it's a very limited number of cases, and usually keeping 3 minutes exposure time for tau images is enough for detecting the electromagnetic emission. A last point we wanted to discuss here is what we call Moon's influence, because one thing which sounded curious at first was that we had less detection of the electromagnetic counterpart for the network, which include the 4 detector, which provide the best localization. And we assume that it was probably because GREM-OPT include a constraint on the angular distance to the moon when you're trying to make images. And to protect the instrument, usually facility are not allowed to get closer than 30 degrees to the moon to avoid, saturating the detector. And what we did to check that hypothesis is to relax this condition to 10 degrees. And then we found that there was a similar detection rate for this neutrino configuration than for the others, which was how we realized that it was probably necessary to not be too shy to get closer to the moon than for the usual follow-up campaigns. This shouldn't be a problem considering how bright these objects are, as we have seen in the previous slides. However, this could be a bigger issue for Rubin, considering how big this telescope is, but this might be mitigated by taking shorter exposure. In the official strategy published by Rubin collaboration, they say that they can get to exposure of 1 second, which give us depth of 22 magnitudes instead of the 24 magnitudes that are provided by the 30-second exposures. And so I think it's more or less the end for this presentation. The thing that we observed based on this study, for which we simulated a galactic supernovae population, is that first there's a strong similarities between follow-up of neutrino of galactic supernova emitting neutrino burst, considering how wide the localization are and how quick we need to be if you want to observe the most interesting parts of the explosion, in particular the shock breakout phase. That it will require a lot of resource to be invested during the blind search phase, which can last for up to 3 days. And based on this, we applied the same strategy we use for following up on gravitational events. And we highlight the role of small facilities that can play an important role in following up on neutrino bursts, as they have more observing time and are more flexible for starting observation. It's easier to start observation with a 20 centimeter instrument rather than changing completely the schedule of a 9 meter aperture instrument such as Rubin. And the fact that these small facilities are usually shallower in their observations is not that of a problem for core-collapse supernovae in galactic planes, since they are very bright and so they are easily detectable. For Rubin, the collaboration also published different strategy when, in case of a galactic supernova happening, detected by neutrinos, and they said that they will follow up on with this number in mind, so about 25 square degrees for a sky map provided by Super Camille Condé, or 100 square degrees if the sky map is provided by triangulation, which, as we have seen with the simulation we have, is probably a bit underestimated. But still, Rubin will be an important facility in case of a follow-up for finding the emission in the optical domain for called galactic supernova detected with neutrinos. Yeah, so that's all for me. I'd be happy to take question if you have some.
Thank you. Any comments or questions to Pierre Alexandre? Okay, maybe I have one. Did you also try to consider like a smaller experiments compared to just like the best case scenario for the neutrinos?
I'm not sure I understand. Did I try what? A small experiment?
Yeah, because like the ones you are using are like the largest scale ones, Juno, Hypercameo Cande.
No, mostly because we use light curve match, which includes basically all those instruments and not the smaller one.
Okay.
Yeah, but I don't think it's completely different, right? So you try, even for smaller detector, you'd have some time of arrival and the sky map produced, and then you try to work around that with optical facilities.
Yep. I see a question on the chat, Santan.
Yeah. Okay, maybe I missed that. I don't know up to which redshift you can detect, but maybe in that case, it's maybe slightly off topic since we are trying to work on galactic supernovae, so redshift is not completely involved. For the further core collapse supernovae they hope to detect with Rubin, I'm not sure. I have an answer right now. But they can go down to 24, 25 magnitude, so I guess it's maybe set equal 2 or 3 easily, but I'm not sure if I have an actual number for that. I mean distance. No. Well, for galactic supernovae, you expect that to detect probably all the galaxy with Rubin. Uh, then you may have some issue with dust, but we have seen that for the distribution I discussed at first, there's no brightness problem or no absorption problem. So I guess it's the whole galaxy for that case.
Yeah, on that point, actually, and I'm struggling. I have a cold right now, so I apologize for how I sound. But you only assumed line of sight extinction, correct?
Mhm.
You didn't take into consideration the extinction of the red supergiants themselves, which can be quite considerable. And I'm just also on that question, to what distance along the plane of the galaxy did you have your events?
So no, the first question is no, we didn't take into account the self-absorptions. Uh, and to which distance? I don't remember the biggest distance, but it was no, I don't remember that. But basically, distance wasn't much of an issue for this work.
I just bring this up. We've been thinking about this for Roman proposals. The Roman Space Telescope's about to launch, and we found non-negligible parameter space where extinction along the plane of the galaxy combined with the extinction of the red supergiants themselves could make it actually inaccessible to Rubin. And you didn't talk about it, but maybe it's enfolded with your numbers. I mean, geographic constraints. You quoted Rubin and also Terra, which I believe is also Southern facility. Is that correct?
No, for tarot, there are three instruments. Two
Right.
are in the two are in northern hemisphere, so TCH and TRE. This one is in northern hemisphere, so it covers
Okay,
basically the whole
I
sky.
didn't catch that point. I was just familiar with their southern components. Anyway, so there's a geographic reach that limits, at least with Rubin and its ability to follow up with that great depth. Did you encounter that in your simulation, or did you assume it could access all the stars?
No, no, no. GWEMUP take into account the position of the
Right.
instrument, so latitude and altitude. So we do not have the northern sky observed in our simulation with Rubin.
Right.
It means that for some sky maps, part of it are not observed, which explain why for significant explain why we do not detect always the supernova, right? For Rubin, like 4/5 only of the injection are recovered. So the other is probably because they are outside the field of
Right.
view and they are not in the accessible sky for Rubin.
And let me just say, this is awesome stuff. This is things we've been thinking about, and there's so many questions to ask, and I could continue asking, but I'll just ask this one more and I'll refer to the paper. Maybe I'll contact you afterwards. The other thing is, did you run this multiple times? Because it's all a matter of when and where, right? So it may be that if it explodes during the day when you have, the sun overhead, it can be very difficult for the a certain observatory to access it, whereas certain vantage points at the side of the Earth may be able to. So I just wondered, did you repeat this multiple times to get these numbers, or did you just go through the year? Um,
Um,
or maybe you just considered, okay, explosion takes place at the beginning of the night. You start observing. I'm just wondering if there was a timestamp associated with this, or you randomly
yeah,
went
so,
throughout.
so basically the neutrino burst that gives the start for the observation is distributed over 10 years. So we generated like 500 GPS time covering 10 years period. We didn't make any constraint that, so it was completely random as it would have happened. And then GWEMUP takes into account the fact that sometimes you have you can't observe with GWEMUP. GWEMUP takes into account the fact that they have daylights and then you can't observe. So that's why you have also part of the sky that are inaccessible because you have basically it's daylight and so on. So we didn't have to repeat that much. It's already included in the tool we are using for the observations.
Okay, you clarified it with your answer about how the simulation was run. I'll have to look at the paper for details. Thank you again.
Yeah, sure.
Thank you. Any other comments or questions?
would spectroscopic follow-up helps? I'm not sure it helps. For what we try to model here and discuss is the blind search phase, when you're trying to look for the electromagnetic counterpart, right? Not complete. It's not about characterizing, the supernova and trying to find like ejecta speed or what's happening in terms of chemical evolution and so on. So spectroscopic, I'm not sure it would help. You would have to be able to pinpoint one specific position to make these spectra. And I'm not sure there will be that much confusion with other transients, since these galactic supernovae are so bright. That said, if the supernova is a little bit faint because of extinction, of maybe self-extinction, as it was mentioned earlier, yeah, maybe in that case, spectroscopic observation would help in order to discriminate, for example, a supernovae with respect to another optical transient, such as a cataclysmic variable, say. But I'm not sure it would be I'm not sure it's completely. It would be the first type of observation I would do for try to find an electromagnetic counterpart. Usually, spectroscopy is more if you want to discriminate between different candidates or fully characterize your event.
If I can add to that one thing, just because it's a rich conversation. So when we had a fire drill with the AVSO members, some of them have modest spectroscopic setups, and they're able to go on the candid stars and be able to monitor. And there's actually a lot of potentially exciting science to be monitoring the spectroscopic changes of the star as it's exploding. But of course, you've got hundreds of candidates to be following up. It's near impossible to do all of them uniformly. But there was a parameter space that we didn't appreciate before, that there are many amateurs and even professional facilities, small aperture, that could be targeting with spectroscopy to look for changes in the signature. Because you mentioned how sometimes you may image the star before shock breakout. So it would be wonderful if we could have a whole time series of what's happening to that star as the shock is inside, and to hopefully capture that time of shock breakout. So that's one of the considerations that we had as well.
Yeah, I agree that amateur observer have an important role to play here. There's now, I think, several network of people trying to observe, external alerts. So for now, it's usually gamma ray burst or gravitational wave sometimes. But I think people would be interested if they can be the first, for example, to observe shock breakout as an amateur astronomer. It would be a huge observation, and also, yeah, to have a continuous observation of different candidates or different region of the sky, provided they have a sky map to guide them. Yeah, it would be also a big player here.
Yeah, that was a very interesting
observation.
part of your result, that you're documenting instances where the observatory was on the actual star before the shock breakout had happened, and then they could return to it at a later time. So at least they'd have a before and after of what was going on. And again, we've never been able to monitor that. Is it totally innocuous? Can you not determine anything, or is there subtle changes in the star that's happening?
Okay. Yeah, that was very nice to see all these capabilities. Any other comments or questions?
Can I have one more question, and then I'm going to shut up?
Sure.
And Marta, I can ask you, I think it was slide 11 where you showed the different localizations, and they didn't all agree. This mildly confused me.
Yeah,
I would hope that there would be a larger localization, but they'd all kind of overlap with the same region. But that's not the case here.
Yeah, because sorry, go on.
Go.
I think the main reason that they are not completely overlapping is because the position of the neutrino detector are not the same. So you have different time of arrival that are compatible with different neutrino detector. For example, IceCube is in this region somewhere. You should have Juno nearby China, AstroParticule in Japan, and ARCA near in Europe. So depending on where the detectors are located when they are observing the burst, you'll have slightly different observing region, but they all overlap around the correct,
Yeah, but
the correct position.
so it's true that actually I was also surprised by that, because what I expect is when you have the 4 experiments, then you have one single ellipse, and then when you have 3, you have 2 possible locations. But the fact that the blue ice cube arc and Super Kamiokande, one of the 2 ellipses overlap, but not the other with ice cube arc Juno. So here you're just switching Super K to Juno, both 20 kilotons, so same statistics, and both in Asia. So, okay, one Japan, one is China, but I don't expect, like, the shift of this orange is very weird.
Is it? Because Juno, the fact that the orange and blue is the red and blue are overlapping is because Super K and Alpha Communicante are basically at the same position, but Juno is not, right? It's in China, not in Japan. So it creates another.
Yeah, it's true. But I was expecting way less angular distance, maybe
right.
between
Okay.
both. But yeah.
Okay, Marta, so you're a little bit, I mean, you noticed that as well, so it's not just me here. Okay.
Yeah. I mean, it all depends somehow what is the time resolution that you are getting, but to get this angular separation for detectors that are not so far away in the... Yeah. Okay. Any other comments or questions?
I have a question from slide 17, I think, about, yeah, you say the timing to get on target. Why? Well, I guess where did those timing values come from? Why does it take LSST so long to get on target?
Well, it's not that long. It can be, but basically it takes sometimes because you have large localization certainties. Like we said, for to cover a 100 square degree localization, it's not that easy. Also, you have to include slew time, so the time it takes to change the position from one painting to another, and I think that's why it takes so long for getting on target. Tau facility are much quicker to move because, like I said, it's robotic 20-centimeter telescopes, not gigantic 9-meter ones. So pointing from one point to another is quicker, and also the Tarot Réunion, which is the instrument which has the largest field of view of the Tarot network, at the field of view of 16 square degree compared to the 10 square degree of Rubin. And I think these 2 facts explain why it's slightly quicker to get in spot with Tarot rather than with Rubin.
Okay. Any last comment or question? Good. Otherwise, we can thank the speaker again.